Undisturbed Earth exists in a state of natural equilibrium. The moment we break ground, we destabilize that physical balance and invite disaster. The stark reality of UK construction is that, on average, 7 people are killed every year working in excavations, with many more suffering life-altering injuries. For the NEBOSH examiner, you must demonstrate a rigorous approach to the 3 primary hazards of excavation work. Candidates must prioritize the mitigation of side collapses, underground service strikes, and falls into the excavation. Survival in a trench relies on precise engineered support and pre-dig detection. Effective safety management goes far beyond general site awareness and relies on technical controls. In this episode, we will sequentially cover the mandatory pre-dig assessment, hazard mechanics, shoring system selection, and the critical threshold where a trench becomes a confined space. Safe excavation relies on the physical engineering of a temporary, stable workspace within a dynamically unstable void. Consider our first scenario, an urban street excavation. Beneath the pedestrian surface lies an extreme density of invisible hazards. The greatest danger here is assumption. Existing utility plans cannot be relied upon for accuracy and must be actively verified. This requires an active detection methodology. Competent persons must use specialized locators, such as a CAT and Jenny, and mark the ground prior to any digging. A CAT, or cable avoidance tool, used with a Jenny signal generator, detects the electromagnetic fields emitted by buried cables and pipes. The examiner expects you to know safe digging practices. Final exposure of the surface must be done by horizontal, manual digging alongside the utility line, never directly above it. The hazard zone also expands vertically. When cranes are used to assemble and remove shoring, they introduce overhead power line hazards, even though the primary work is below ground. Horizontally, digging too close to adjacent structures can undermine their foundations, causing secondary collapses of entire buildings. On brownfield sites, we face the legacy risk of contaminated ground. This includes decades of accumulated industrial chemicals, solvents, and previously buried waste. Disturbing contaminated soil has severe knock-on effects. Intrusive works allow surface pollutants to migrate into deeper groundwater, and sulfate contamination in the soil can actively weaken the concrete used in your construction. Breaking ground blindly is indefensible. The pre-dig assessment dictates the entire physical, environmental, and operational control strategy for the project. Moving to Scenario 2, a deep trench in poor ground after heavy rain. The primary failure mechanism here is the weight of infirm, cohesive, or granular soil detaching from the trench wall. Cohesive soil remains in clumps when dug, while granular soil breaks up easily and will not hold a vertical face. This is an animated diagram showing a 3D cross-section of a trench. Notice the catastrophic role of water ingress. Water from adjacent courses or heavy rain lubricates the soil's slip plane, guaranteeing instability and triggering a collapse. Battering, which involves sloping or stepping the trench sides to a safe angle, is often the first control measure considered. However, it has strict limitations. It requires massive surface space and fails completely in oozing mud or running clean sand. Trench boxes and drag shields offer a different approach. These are non-urban, rapid solutions that protect the workers inside the box, though they do not actively prevent the surrounding ground from moving. We contrast shields with slide rail systems and whaler frames. These systems use hydraulic rams to apply active outward pressure against the earth. By physically pushing back against the soil, they prevent settlement, making them ideal for urban environments up to 7 meters deep. This illustrates sheet piling. These are interlocking steel sheets driven into the ground prior to excavation. They excel at forming a watertight barrier to control groundwater. Despite their effectiveness, sheet piles have severe disadvantages. They cause logistical delays, carry high rental costs, generate massive noise pollution during installation, and are extremely vulnerable to underground obstructions which split their interlocks. To manage groundwater, contractors use dewatering. A simple sump pump removes water from within the trench, while well point dewatering actively lowers the local water table, removing groundwater directly from the soil before it even reaches the excavation. Any pumped water requires strict environmental controls. You must conduct testing to differentiate between a harmless bacterial sheen, which breaks into irregular pieces when disturbed, and hazardous oil contamination, which stays intact as a constant layer and must be disposed of as hazardous waste. This photograph shows the scale and complexity of urban excavation projects. Look at the heavy machinery and the required retaining walls. Shoring selection is not a contractor preference. It is a strict engineering calculation that must perfectly match the specific shield technology to the localized soil and water conditions. Transitioning back to the surface edge, we must implement perimeter controls to prevent falls. Gangways and working edges require guardrails at least 995 mm high and toe boards 150 mm high. We must also eliminate the hazard of surcharge loading. Excavated spoil heaps and imported materials must be set significantly back from the trench edge to avoid adding a crippling weight burden to the trench walls. For vehicle and pedestrian controls, the mandatory use of stop blocks keeps plant vehicles safely away from the edge. Additionally, designated crossing points for personnel must be a minimum of 430 mm wide. There are strict rules for access and egress. Ladders must project a minimum of 1 meter above ground level. Climbing in and out using shoring struts or wailings is absolutely prohibited. The NEBOSH examiner will test your knowledge of the statutory inspection regime. A competent person must inspect the excavation at 3 distinct triggers: at the start of every shift before work begins, after any event likely to affect stability, like heavy rain, and after any accidental fall of rock or earth. The reporting legalities are rigid. A written report must be generated within 24 hours of the inspection, a copy must be kept for 3 months, and work must stop immediately if the excavation is deemed unsafe. Perimeter controls prevent the initial fall, but the relentless, documented daily inspection regime is what actually validates the engineering and keeps the trench viable. This historic photograph shows the physical reality of deep, enclosed subterranean work. It sets the stakes for our third scenario: chamber entry. The Confined Spaces Regulations 1997 classify a confined space as any enclosed place where a specified risk is reasonably foreseeable. These specified risks are lethal. They include toxic atmospheres, explosive gases, oxygen deficiency, extremes of temperature, and the risk of drowning in free-flowing solids like cement powder. Atmospheric hazards in trenches are insidious. Heavy gases like hydrogen sulfide or carbon dioxide can pool at the bottom of a deep trench, silently displacing oxygen until a worker suffocates. This necessitates a strict permit-to-work procedure. Step 1, and the absolute first principle of the regulations, is to avoid entry altogether by working from the outside if reasonably practicable. Step 2 is the testing protocol. Atmospheric tests for oxygen content, flammables, and toxic gases must be conducted at multiple levels before entry because gas concentrates at different depths. Step 3 covers operational controls. This includes isolating and locking off mechanical plant, requiring continuous gas monitors on the worker's person to trigger audible alarms, and utilizing mechanical ventilation blowers to push fresh air into the space. Confined space emergencies are unforgiving. Heroic, unplanned rescue attempts frequently lead to multiple fatalities. The tragedy at the Carsington Dam project is a permanent reminder of the cost of failing to follow life-preserving rescue rules. Mandatory emergency arrangements must be established before work starts. A rescue plan must be fully equipped with tripods, winches, full body harnesses, and breathing apparatus. You cannot rely on calling public emergency services to extract an unconscious worker from a toxic environment. Entering a confined space introduces distinct chemical hazards that simple trench awareness cannot mitigate. Management requires a locked-down permit system. To synthesize the core operational reality, a compliant site anticipates failure. Here is a second critical mistake. Writing "Call 999" as your confined space rescue plan will fail you. The ground wants to collapse, plans lie about utilities, and voids accumulate gas. Don't confuse drag boxes with active systems like whaler frames. Shields only protect workers inside. Whaler frames actively pressurize and support the ground itself. The site must have its own non-entry rescue equipment ready for immediate deployment. Finally, remember that daily inspections are a strict legal trigger. They are mandatory validations of the trench's safety. When faced with an excavation scenario in your exam, build your answer chronologically. Detect utilities, secure the surface perimeter, engineer the shoring based on soil, and lock down the atmosphere. Passing this element requires proving you can sequentially build physical and procedural layers of defense to conquer the absolute unpredictability of the ground beneath us.